Designing future APIs based on Isology, the study of references, standards, and standardization. So this, all right, next screen, please. Next screen. Hello.
Joseph?
Yeah.
Hello.
You're not seeing the screen?
Okay, there we go. Okay. Evolution of technology. This is a different way of looking at technology than I suspect any in the audience have experienced before. But let me just say that we can look at history in a myriad of ways: the wars, the governments, the political systems, the social systems, et cetera, and I'm proposing a way of looking at history based on technology, and in particular, the standardization of technology. And I'm using the term standardization very, very loosely as describing those things that emerge commonly and what we tend to call as references before we call them standards. So let's say 10,000 years BCE, this concept of symbols has emerged. And we can see that in cave art, where we see symbols of animals that are hunted. We even see symbols of people's hands. Probably the first picture, I am here, this is my hand. And so these symbols start to emerge very early. And I suspect, and a number of notable archaeologists suspect, that these symbols are the beginning of communications and bartering, that the real purpose of these symbols is to say what's available, and therefore valuable for bartering purposes. So the next succession of standards emerges with measurements. And measurements are key to the development of agriculture. Agriculture, in order to feed a group of people, you need to define an area and provide the appropriate number of plants or seeds in that area to feed the people. So you've got to start counting and measuring. And that counting and measuring coexist with the beginnings of agriculture. Oh, let's go back.
Sorry.
Okay. The idea here is there are 6 identifiable successions of standards, which really represent the evolution of technology. For those of you who may recall, a gentleman by the name of Alan Toffler proposed the third wave, and he recognized an early time, which he called hunter-gatherer, then agriculture, manufacturing, and then he called it the information age. And I've tried to make it clearer and just say programmable things. So those first 3 were widely discussed in the 60s, 1960s, when he wrote his book. The other 3 that I've inserted, bartering, building, and networking, I believe fit the models described. But anyway, these are all obviously my opinions of the evolution of technology. The interesting thing to me here is that this is based on set theory. Symbols are the points in a set. Measurements are how we quantify those points, and the set itself is a design or a plan. And then in similarity, this is a similarity between sets, the compatibility of sets, and then the adaptability of sets. So this is effectively a mathematically based model of the evolution of technology. So after measurements, the next succession is designs or plans. And an interesting point here with building is the 7 great wonders of the world, which began around the 3000 BCE, were all buildings. They were not the Grand Canyon or the Alps or some other landmark. They were the product of people's designs, and obviously people in great power. So with building, we see the emanation of designs and plans. And then manufacturing, we see the beginnings of similarity. Think about it, and any manufacturing process is producing repetitive results, which are obviously similar. So the concept of similarity and manufacturing go hand in hand. Next, networking and compatibility, I suggest, emerges around 1800 with the beginnings of interconnected railroads. And that's kind of the time when we start to see standardization actually occur, where there are standards for the spacing of the train track, 4 feet, 8.5 inches. Around 2000, I suggest that programming moves from just a device that makes operations easier to a mechanism of interacting. In 2000, according to the little bit of research I've done, the first smartphone connected to the internet. So, or a early version of what is now called the smartphone connected to the internet. So a programmable device connected to a programmable system. And that, I suggest, is the beginnings of adaptability. And the purpose of this talk is to describe how adaptability affects the operation of interfaces. But I'm going to go a little bit further. So Joseph, if you could go to the next slide, please. There we go. Okay, so I'm trying to give a little more detail to the successions of references and standards. The symbols, as I mentioned, the purpose is to identify, to recognize, and the effect is to recognize and to barter. With measurement, the earliest use of symbols with measurement is obviously numbers, and later on currency. And the function here is to quantify. And this is the basis of agriculture, and this is the basis of trade. And where I'm using trade as the formal mechanism where we use numbers and we no longer just barter, which is to exchange goods. So the next succession of standards emerge with designs and plans, and where we create the wonders of the world. And we also create ships and various things, TPs, which are no longer simply attempts, but they are built on a standardized form. Obviously, the standard hasn't yet been written down, but people have recognized how to build teepees, how to build lean-tos, how to build dugouts, how to build even larger ships, which are beginning around this period of time. And then next succession of standards is similarity. I used the data 1400 for the beginnings of similarity standards because in Venice, Italy, at a facility called the Arsenal, in the early 1400s, the acts of standardizing things were formalized for the first time that I'm aware of. And so Venetian galleys could be produced in the Arsenal at a rate of 1 per week. To give you some idea of how significant that was, in Corsica, which is at a similar latitude, not so far away, the rate of production of a galley from the shipyard in Corsica was 1 per year. The rate of production in Venice was 1 per week. That was created by similarity standards. In fact, if you go to the Venice Arsenal today, you can actually walk into a room and see in the stone floor, the shape of a wooden rib of a Venetian galley. It was that shape that was copied by the people who worked in that room to make other ribs, so that the ribs could be put together into a boat with oars and rudders and all the other accoutrements of these galleys in a 1 week time. And in fact, there's actually at the Venice Arsenal a clear plan of the how the industrial production worked, where the ship moved through successive rooms being outfitted along the way. So this was the beginnings of industrial production, way before the Ford Motor Company, as example. Now, it's important to note that today, similarity is extremely important to pharmaceutical companies. They invest hundreds of millions of dollars in the design and testing of drugs for human use. And because of that, they are very committed to the need for patents to control their similarity, the similarity of the chemical structure or the similarity of the process. And so we see patents being very important to the success of pharmaceutical companies and their ability to invest the kind of money that they must in order to produce successful drugs that have been tested for safety and efficacy. So this is the similarity. And in fact, in the Venice, Italy, the first patent, what we now call a patent, was created. And because the builders there, which was the Medici family, the wealthiest family in the world at that time, used these galleys to control trade in the Mediterranean, which was the wealthiest part of the world, and therefore became incredibly wealthy themselves. So again, the indications here are the incredible value of controlling similarity and the need now in modern times for similarity to be controlled, at least in certain industries. Moving onward to compatibility, which I suggest arises around 1800 and continues to this day. We have the air interface for cellular systems, railway gauge, as I mentioned. Joseph mentioned group 3 facsimile, which has some very interesting aspects and was extremely successful for about 40 or 50 years, obviously before the internet, at providing some form of communications in a written mechanism. The Gillette razor is a wonderful example of compatibility. You may recall the safety razor, and if you look at it, it has a very curious shape. The blue blade has all these cutouts in it. And I'd like to explain why those cutouts occurred, because it represents an extremely good example of what compatibility means in a business situation. The simple way of thinking about the Gillette razor is the marketing idea that you give away the razor and sell the blades, which is exactly what Mr. Gillette did. And we have lots of documentation about what he did because he submitted a patent for his first safety razor. And the blade that was in it just had a little hole in the center where a threaded screw went to hold the two parts of the razor together to clamp the blade. And there were two notches on either side of the hole spread out so that the blade wouldn't rotate around the pivot point. And that was the shape included in his patent, not the shape that we're familiar with today. The reason for that is that once the Gillette company started to give away the razors and sell the blades, competitors emerged because it turned out to be a good technology, much safer than the standard razor of the time. This was now called the safety razor. So the competitors, recognizing an opportunity, built blades identical to the shape of the Gillette razor blades. And in fact, there are ads from such competitors that exist, which show at the bottom a little type compatible with Gillette safety razor. So Mr. Gillette, in order to preserve his market advantage and not be undercut on price by people who were taking advantage of the fact that he gave away the razors, introduced blades with more holes in them, and he had some square holes, and his new razors, which he gave away, had square holes in them. So think about this for a second. The old blades would work in the old blades from Gillette would work in the old razors, but the new blades from Gillette would work in the new razors as well as the old razors because they had more holes in them than the older blades. But of course, his competitors were not ignorant people, and they rapidly changed their manufacturing product to include the new holes. This upset Mr. Gillette a great deal, and he tried on several occasions to make more holes in his safety razors. And he started a process of submitting to the United States Patent and Trademark Office a trademark on the shape of his blade. But the initial trademark office response was that you can't trademark a shape. And so they rejected his requirement, and he was faced with his competitors continuing to produce blades that undercut him in price. So he then finally produced a very complex shape, which had the squares and triangles and so forth that we see today. And that shape, the trademark office finally agreed to trademark. And that allowed Mr. Gillette to sue his competitors for trademark abuse and prevent them from selling in competition to him. That is the nature of compatibility. Compatibility, when controlled, creates enormously successful markets, as Mr. Gillette demonstrated totally mechanically. Railway gauges did the same. And the air interfaces now, we actually work very hard to standardize air interfaces, but the idea that there are patents on those interfaces cause large costs to be passed through to the consumer for hundreds and even thousands of patents now on these very complex air interfaces. And moving into the more current times, we have APIs, applications programming interfaces, which I'm using here really as software interfaces, interface between two piles of software that are doing some process that's related. And so these are what we have today is communications with control. And I propose, based on the diagram I showed you previously, that the next succession of standards are adaptable standards, where we use terms like machine learning, and we have discovery protocols like plug and play, and we now have less control and what is a new term, emerging openness. Next slide, please. To make the point about the difference between similarity and compatibility, and also the complexity, this is a very simple picture. These are two mechanical shapes. Plug 1 and plug 2 are obviously similar. Socket 1 and socket 2 are obviously similar. And so if we have a specific plug and we can patent it for some reason, we can control the ability to make other plugs, but we also control the compatibility of that plug with a socket. So compatibility was never something that was understood when in Venice in 1400, the first patents emerged. The idea was if you could show how to make a better oar or a better rib or a better mast, then it was worth something and we were willing to pay you. We, the Medicis, who owned that plant, were willing to pay you for that value. In fact, the first patent is on a crane that was used on a barge to move rocks for sculpting. And the complexity of that crane was patented. So give you some idea. So now putting this in some more current form, the idea of similarity, as I mentioned, is extremely important to the pharmaceutical industry. It basically allows them to go through the incredible costs necessary to prove the safety and efficacy of a drug. Without a patent system, we would probably be unable to have the quality of medicines that we have today. So that's an indication of how significant a patent system is to human beings. On the other hand, we probably know, or many of you do, that compatibility is something that is a requirement for communications by Google or Facebook or Amazon, whoever it might, whatever company, and they dislike the idea that they must pass on to their customers charges for compatibility, when compatibility is usually a agreement, not a invention. And that concept is not understood in law, in patent law at all. And so to raise one's hand in a patent court and say that issue is associated with agreement, not invention, would be basically laughed out of court. And so this gives you some idea of the confusion that occurs in our patent system and commercial system, where one kind of company finds similarity absolutely necessary, and another kind of company finds compatibility to be patents on compatibility to be a tax. And so next slide, please. So the economics of standards. Similarity creates efficiency, and it creates the ability to make investment in many cases. Whereas compatibility, the economics term creates network effects. Network effects means that if you create a telephone system like Alexander Graham Bell did between a doctor's office and a pharmacy, which was the actual first sold system of Alexander Graham Bell, then another pharmacist wants to connect to that same system to talk to that doctor, and another doctor wants to talk to that same system to talk to the pharmacy. So once the first system is installed, this idea that all the other people around want to use the same system becomes a driving force, and that's called in economics network effects. And so now I propose that adaptability reduces network effects with openness. And once we have programmable devices, the idea of creating adaptable interfaces, not devices where we do conversions, which are rather fixed, but adaptable, programmable devices where they adapt to operate differently when programmed to do so. Next slide, please. In the internet, to talk about openness is a little more complicated. I'm hopeful that many of you are familiar with the OSI model, which is a 7-layered structure. And these layers effectively are all associated with compatibility. So imagine these 7 layers being adjustments or separate variables in the succession of standards, which I've termed compatibility. So the 7 layers of compatibility that occur in an OSI model, the physical layer, the data link layer, the IP layer, the TCP UDP layer, layer 4, layer 5 is the session layer, layer 6 is the presentation layer, and the top layer, layer 7, is the application layer. Now this is I just listed the OSI model. The internet model, interestingly enough, has only 5 layers. The physical layer, the data link layer, the IP layer, the TCP UDP layer, and the application layer. There is no session layer or presentation layer. A little digression is that with a lack of a session layer is the reason why security does not exist in the internet. There is no session description in the internet. It has to be added by the applications that use the internet. And there are, of course, many applications which do provide security, but they provide it end to end, not within. It is not a network requirement. And the same with presentation. Presentation is not a network requirement either, and it's provided by the end units. And that's why we've had many difficulties with issues like voice compatibility, voice codec compatibility, and video codec compatibility. Presentation layer functions that could be negotiated at the presentation layer if there was such a capability in the internet. For reasons of simplicity, as well as moving complex functions out of the network and to the end units, which makes a lot of sense, the internet was designed with 5 layers. And so when we talk about compatibility with the internet, we basically, at the bottom layer, the communications, we negotiate to provide a compatible IP structure, support for a compatible IP structure. And at the application layer, we negotiate to provide support for the TCP UDP layer, which in general in OSI terms is called the network layer. The idea of how we negotiate compatibility is kind of flipped in the internet, and that's a huge advantage of the internet, which has worked extremely well. Let's see, is anyone monitoring the chat lines to make sure that everybody's in good shape?
I am monitoring.
Good, thank you.
So I send a message to let people know.
Okay, excellent. Okay, Joseph, could you go to the next slide, please?
Yeah. There's let's see. Frank Lemon said retired. Oh, he just said I sent an introduction. Okay, no, never mind. Wasn't a question.
Okay, so now I'm thinking that many people came to this conference or webinar to discuss software interfaces, which I'm using the general term APIs to describe. Currently, software interfaces are thought of as private, partner, and public. There's an excellent discussion of APIs on the Wikipedia, and I'm just really speaking from that to describe, the common view. And I propose with public, of course, people would describe those software interfaces as being open. I'm suggesting that when we have programmable interfaces, we can look at the openness and control it, and control it basically for 2 reasons. One is revisions and one is private functions. So an adaptable interface, it can have openness, but it also can have private functions. And that, I hope you'll understand from what I've explained, is a very powerful way to move the desire for commercial control from patents into the interface itself. As example, if we had 2 video systems that wanted to talk, they could negotiate, if such a protocol was available, such an adaptable protocol was available, what video codec to use. And they might choose video codecs based on cost or performance, or performance meaning pell densities, or performance meaning latency, or performance meaning color or black and white, and all the different variables that might occur with a video codec. Those could be negotiated. And those mathematicians, scientists who created video codecs, which offered some unique capability that was better than the other video codecs, could effectively control the market for that codec by negotiating the use of it. As example, it is legally acceptable that the trademark General Motors is owned by General Motors, and that one cannot use it, that name for profit without a license from the company General Motors. So if you have an adaptable system, the way it can operate is that one end sends a trademark name to the other end, which when it sees it and it's capable, responds with the same trademark name back, in which case the 2 systems operate in their private mode, which may be a charged mode or allow for only special people who have previously signed up for this capability. So what I'm offering here is a suggestion that we can start to think about software interfaces, not just as private, partner, or public, but as capable of supporting both public and private functionality. And another clever way of going about it, also supporting revisions. Now here, the difficulty we have with communications and communications APIs or protocols is that technology often changes. New features emerge, new capabilities, new operations, etc. And it's difficult to make such operations backward compatible. And so I'd like to go back to the group 3 facsimile work, which I was involved in for many years, and suggest how that was done. In the group 3 facsimile work, a separate means of negotiation was created, which was called T.30, from the data channel, which was called T.4. And so all negotiations of what was passing across the data channel was accomplished in a separate channel called T.30. By virtue of using this separate channel, we negotiated a single tree structure logic. So there would be a branch on the tree which was color. There would be a branch on the tree which was Pell density. There would be a branch on the tree which was compression type, et cetera, et cetera, et cetera. And you could extend these branches of the tree. You would never remove any branch of the tree, but all you're talking about is a tree with code points. So even at the 300 bit per second rate of group 3 facsimile control functions, you had plenty of data rate to support the various code points that you needed in this tree. And by virtue of having a single logical tree structure to negotiate backward and forward compatibility, you were mathematically certain that you would have backward and forward compatibility. If the capability existed, you could negotiate it backward and forward. And that worked extraordinarily well for 40 years of group 3 facsimile. So I'm basically proposing that logical construction return to adaptable interfaces which need to be backward and forward compatible. So two different thoughts. One is how to maintain an interface backward and forward compatible, and two is how to provide private functions for profit of private organizations. Next slide, please. So openness supports both public and private operation via an interface between two programmable systems. No longer is openness only public, which effectively disadvantages engineers like us who make our living by designing things that can be patented. But it now allows for us to make a living, as well as the public to use the system to the extent that they're willing to. Okay, next slide, which is the end. Thank you. And hopefully we can take questions. I see nobody else on my screen, so it might be hard, but I hope so.
So
Frank Lemon?
let me see how you can see everyone, because I changed everyone to be a panelist. So you should be able to go into the top right-hand corner and let me stop sharing. There's a
Okay,
view.
now I've got everybody. Okay, good.
Yeah. So everybody, now you can unmute yourself. If you have questions, feel free to ask Ken at this point.
Looks like Frank has his hand raised. Maybe he has a question.
Yes. Frank, go ahead.
Hi, this is a really interesting presentation, especially with the hierarchy of isology over the centuries and decades and so forth. It is a distinctive way of looking at things. One question I have about APIs, the technology of APIs seems to continue to evolve. I don't think we've hit a point where there's enough stabilization in the technology itself to permit standardizing on a particular technology. It's been tried several times before, with starting with remote procedure calls, then it went to XML, and then currently it's at REST, which is
Right.
yeah.
And there was an earlier attempt at SOAP as well.
Yeah, SOAP is XML basically.
Right.
Yeah.
So yes, and now it appears, at least in my little experience, to be more REST oriented. But that's not important. Basically, we basically pick a different API, if you will, as opposed to an existing API. And we use that only for negotiation purposes of any other API. And we maintain that API because we don't really care about its performance. We only care that it supports a single logical tree structure. Make sense?
Okay.
It is a very different way of designing a system. But I'm proposing that basically it is the way we should think about designing when both sides of the interface are programmable.
So one thing that occurred to me thinking in that context is do you think that blockchain could be used to provide a decentralized, what did you call it?
Negotiation.
Yeah, well, no, a decentralized adaptable system for
Well,
API openness.
Certainly it could. I don't know. I'm not a huge fan of blockchain technically. The idea that machine cycles are the way I'm going to value the system strikes me as a disaster.
Interesting.
So yes, there's no question that blockchain could be used. I've seen no reason why such an inefficient approach to valuing the system. I can create security codes of extreme complexity for far, far less resource than what blockchain uses.
Okay.
So there's a question from Tom Coughlin to Ken. You've made an analogy to set theory in terms of technology development. Would you also describe the roles of API in a mathematical way?
Well, I'm a believer that if you're smart enough, you could. I am not smart enough. So I agree with the theory, but I don't know how to do it. So APIs, in my mind, are just the interface between programmable systems, no different in that sense than the plug and the socket. The only issue is we now have a plug and socket, which can be any size, shape we want, anytime we want it. And I guess I've mentioned two other differences. One of which is I can now offer a form of legal control across the interface, which I only had patent control before. And now effectively I'm offering trademark control across the interface. And the other aspect is by thinking in terms of a single logical tree structure, I can offer basically infinite backward and forward compatibility. Near infinite is probably a better word.
Anybody have questions? You're free to open your mic or you can post it in the chat. So earlier, Ken, when you and I spoke, now with API provide a standard interface, you also mentioned there's still a way that you can create a differentiation using standard APIs. Could you expand that a little bit?
I tried to by saying that you can differentiate by sending back and forth a unique trademark between the two systems that wish to communicate. A good example right now is that there are three major distributed cloud computing systems, the AWS, the Google, and Facebook. So these systems are incompatible with each other. Mostly because each of these vendors wishes to have an incompatible interface because they want to control their market. I mean, and that we shouldn't argue that that's a bad thing to do. The capitalist motivation has been very successful, and making it go away is not likely to improve things greatly. So what I propose is that those three companies could get together and agree on how to negotiate which cloud computing interface is to be used in any given circumstance, and make that negotiation a freely available capability. So then, obviously, since it's programmable, it wouldn't be that hard to either go to a known website and download the API that works with each particular cloud computing system, or to have the whole range of them stored in some program on your system. I see another question.
Yes, also coming from Tom Coughlin. So do you see an element of this stage being self-evolving APIs? If so, what are the limits to this evolution?
I do see it as a self-evolving system. I'm proposing a set of ideas which strike me, at least, as being clearly derived from the past. So I feel strongly that they're occurring. Obviously, I am not watching every possible interface standard, and I said every time I look at new interfaces, I see them getting closer and closer to what I'm suggesting. So the theory of isology, much like any good theory, allows the practice of interface design to be more rigorous. And we don't have to design interfaces based on how we did it before. We actually have a theory that allows us to say, oh, these are the new directions I could take it. And that's what I'm proposing for the people here. I've written tons of papers on this stuff, and you can find papers on isology.com on a lot of this for sure.
Okay, thanks. Any questions from the audience? If there's no more questions, do people just want to give open their mic and just give a quick introduction, since I think majority are life members, so you guys haven't really met because of the pandemic, and also I think the life members didn't have much many events even before the pandemic, so we have a few minutes with Zoom, so feel free. I think Frank, you make an introduction on chat. Anybody else?
Well, I'm Tom Coughlin. I asked a couple of questions there, so it's a pleasure to hear you and to get your theories. It's a very interesting concepts, and I'm still working. I'm not retired, although I did become a life member. Work in digital storage and memory, and also been a IEEE volunteer in many ways, and still doing that.
Yes. Yes, as an IEEE member, I voted for you on occasion.
Thank you.
Right.
Appreciate it.
I have a question for Ken. Frank here. Can I ask?
Please.
Okay, so I'm trying to get my head around this in terms of real technologies that have evolved over decades. And one that comes to mind is the World Wide Web itself. That seemed to evolve in a more predictable fashion, and it seems to fit your model a little better. Do you see the web itself, and maybe like the HTTP protocol, being a good example of isology in action?
Oh yes, for sure. Interestingly enough, it evolved, as I showed in the slide, the so-called hourglass slide, that the internet took off because it created a different model of compatibility. It had the network separated from the network layers, separated from the application layers, and so that allowed this. Whereas previously the phone company, if you will, was talking about having to offer compatibility at each of 7 layers. And this is what killed the ISDN basically, was that the phone company, and I was, by the way, on many of these committees, and I was very confused about it. And that really is what started me thinking about what I've just explained to you. I would come from a group 3 facsimile meeting where I could make anything compatible with anything. And I would go to an ISDN meeting because that was my business. I was consulting for companies to help them in standards work. and I couldn't make anything work with anything in ISDN. And it took me the longest time, literally years, to try to figure out how in one meeting with oftentimes similar people, I could figure out how to make anything connect to anything. And in the other meeting, I couldn't figure out how to make anything connect to anything.
Interesting.
And so the internet came along with a different model. And by the way, the hourglass picture that I showed really comes from David Clark, an MIT professor who was very active in the internet early on. And it was he who noted this is how the internet worked, but I think it was accidental. I don't think anyone, when they were conceiving the system, fully thought through the idea of having compatibility built from the bottom up and the top down with a continuous standardized middle. That was a totally new idea. And yes, it does certainly show the success of the model that I proposed of successions. Another interesting way of thinking about these models is if you imagine a world clock kind of face, a clock face, where the great idea occurs at 12 o'clock, and the implementation occurs at 6 o'clock, let's say, then I suggest that on the right-hand side of our clock face, the numbers 1, 2, and 3 are the anticipatory standards development cycle. I've got a great idea, but I need a standard. And if you're talking about standardizing physical layer, the size of the wire, the size of the connector, the number of pins on the connector, you have to get agreement on those things before you can make communications happen. So those standards all become anticipatory standards. And the organization that basically is most famous for doing them is the ITU, the International Telecommunications Union, because in order to have telecommunications like telegraph, which is where the ITU started, you've got to standardize stuff before you build it. On the other hand, before the IETF emerged and the whole internet emerged even before the web, the other form of standardization was around the numbers 9, 10, 11, and 12, which was responsive standardization. IBM, as example, during that period had produced things like BiSync, and many systems used BiSync. And so the other companies who were trying to compete with IBM, like Sperry and Univac and so on, Burroughs, et cetera, wanted a common standard for what BiSync was. They didn't want to say, I use the IBM way, and they didn't want IBM to change it in the middle if they had built it that way. So they went to ISO to make standards on the IBM equipment. So this is responsive standardization, where the standard occurs after the product, later in the cycle, way past development side, where basically I've said the idea occurs at 12 o'clock and the product first emerges at 6 o'clock. So the magic about the IETF and the internet was that they produced a model which was participatory standardization. So the IETF said you have to have 2 running implementations in order to work. Well, now let's be serious. If you that's impossible to do in a telephone system, which is at the physical layer. You have to agree before you can make something. But once you have the middle layers chosen, you can certainly decide what network you want and how it works, or what applications you want and how they work, and make those implementations participatory while you're making the product. So effectively in our little clock face, the times like 4, 5, 6, 7, 8 are the participatory standardization period. That was the great invention of the IETF. And interestingly enough, the IETF has no idea that that's true. This is all new news to them.
Yeah, I think it's fascinating the way that different technologies have evolved either very cleanly into standards or completely a mess. You know, the big mess that I think of is I/O connection interfaces to computers. You know, you've got Apple off doing their own thing for a large part, and then you've got everybody else on the PC side doing their own thing with USB and USB 3.0. And it seems now like they're sort of moving towards the common bus standard, but the connectors are still out of whack. But then you look at other technologies like.
Let me offer some alternates. If you look at AC plugs, same problem. It's getting
True.
better, obviously,
True.
in Europe. But the manufacturers wanted to control things throughout history.
Uh-huh.
And in fact, I can offer an anecdote here. I had about an hour-long conversation with Steve Jobs in the mid 60s. His company, Apple Computer, was starting to get known, and my company that I was working for at the time was called Vedic, and we made data modems. And I went to Steve Jobs to try to sell him on buying our data modems, which would require that he had a standardized interface, which in those days was called EIA 232. And I proposed this to Steve, and he's a bright man, and he spent a good deal of time listening to my proposal. And he said basically, absolutely no, I want to control the interface. And I don't think Apple has changed their mind. And I point out that he's been very successful doing exactly that, controlling the interface, which has made his company the wealthiest company in the world, but has not been of great value to those of us who try to. I've got a little adapter on my desk, this thing, whose purpose is to make my Apple computer work with most of the things that I want it to work with.
Yeah.
So the adaptable interfaces is a mechanism to allow Steve Jobs to do exactly what he wants to do, and allow us to agree whether or not we wish to pay for it, depending upon how well he does what he does.
Mm-hmm.
So that's the power. Any other comments? Yes. Oh, I suspect that might just be someone's mic on, right? Okay. Joseph, over to you.
Sorry about
Joseph?
that. I was on. Okay, I think if we don't have any other question, we can just end the webinar tonight.
All right. Well, thank you. I thank everyone for taking the time. I always enjoy talking about this.
All right. Thank you very much.
Thank you
Have a
all.
good night, everyone.
Thank
Good
you.
night.
Thank you.
Thank you.
You.
Thank you. Good night.
Good night.